Okay, last time I was going through the Liberty library format, which is the format we use for capturing timing information for the cells in the library. And I will quickly summarize what we saw last time. But before that, I thought I would just go over some nomenclature, so that all communication in this class and and also in your professional life as an ASIC designer is done with clarity. Nomenclature, using the right nomenclature is very important. And instructors sometimes assume that the nomenclature is known, but often I notice people mixing up terms. So I just thought I'd spend a few seconds clarifying the nomenclature of this field. And specifically, I'm going to just quickly go over the nomenclature that's relevant to netlist. So first of all, the netlist itself, as I may have said last time, is a textual representation of a circuit. Any circuit that you represent in text format that file is called a netlist file. So in netlist, we have the following nomenclature is important. So what are instances? Instances are, so in a standard cell library, you have all kinds of gates, and any gate may be used multiple times. Each time the gate is used, we say it's an instance of that gate, and every instance has a unique name in a netlist. So cells are obviously not unique because the same cell will be used multiple times, but every instance has to have a unique instance name. So in this particular example here, you can see there are two input NAND gates, and they're both the same standard cell from the library, but they're different instances, and we give them the unique instance name. So one is called U2 and one is called DM. Then pins are the actual physical objects to which at which you make connections to a standard cell. Okay, and then pins have their own names. So typically in a standard cell library, there will be some naming convention for pins. So in this example here, this combinational cells, I'm saying the input pins are names A, B, and so on, and the output pin is called Y. But of course, every standard cell library will have its own naming convention. So pins are where you actually make connections to a standard cell. Okay. Then ports are the primary inputs and outputs, and it's important to keep this distinction. To maintain this distinction, pins and ports are different things. Pins are where you make connections to standard cells. Ports are where you make connections. Ports are the actual input-output inputs and outputs of the whole circuit. So pins and ports are different, and when you use tools like Genus and Tempest, all these cadence tools or Synopsys tools for processing netlists, there will be different commands to deal with pins and ports. And what are nets? Nets are the actual connections of pins, okay, or the wires. So nets, in this example here, every wire that you see, every kind of every connection is a net. So, and each net has its own name in the net list. So, for example, the net N1 is the net that connects the instances U1, U2, and this flip-flop instance. So that's the net N1. Okay, and then you can see there are different net names, and the net names, instance names, they can be any sort of names. Sometimes they are very long in the net list, but all nets, each net has a unique name. A net has a logical view and a physical view. What is the logical view of a net? So logically, a net is nothing but a set of pins that it connects. Okay, so the net N1 is U1Y, U2B, and then the flip-flop reg_demux D, the D pin of that register. So these three pins, the Y pin of the U1 and the D and B pins of the other instances, that set of those three pins constitutes the net N1. That is the logical view of the net N1. Then the physical view, net N1 will also have a physical view, and which is the actual physical wire comprising metal shapes and vias that results in this net being physically implemented. Okay, so any net has a logical view and it has a physical view. The initial net list will have all the nets will have only a logical view, but as place and route is done, as routing is completed, the net will have a physical view. And then there is and then you have to be familiar with the term drivers. Every net has a driver, okay, and the driver is what drives the net, and then the net itself, the driven net, is then connected to multiple standard cells, which would be receivers. Okay, but it's important to correctly use the term driver, and every driver is either an instance or is the pin of an instance. So these are used interchangeably. So for the net N1, the driver is the two input AND gate U1. Okay, or you can say that the driving pin of net N1 is U1/Y, the Y pin of U1. So I want you to be very clear about this nomenclature and to use it correctly. And this nomenclature is also built into the commands that the tools use. Okay, so let's get back to where we were last time. So last time I went through, I was going through the Liberty model of a standard cell, and as I said, I'll go into a little bit more detail this time, and then we will move on to the other text files or other files that are used here to describe standard cells. So currently we're talking about the Liberty file or the Liberty model, sometimes called the .lib model. And as I said last time, this model contains the timing properties and other electrical properties of standard cells. And also the functionality of the standard cell is in the Liberty file. Now the Liberty file contains delays. So in a combinational cell, the delay is from input to output. I defined what the delay is last time. How do we know the delay through a gate in a logic path? These cells, this particular standard cell, is from deck of slides by Dr. Adam Tiemann from Bar Ilam University in Israel. I've just used those for this next few for the next few slides. How do we know the delay through a gate in a logic path? In principle, you could run a SPICE simulation for your whole circuit, but that would take too much time. It's way too complex. So we create these timing models that are Liberty files. And what is done is in order to get that timing information that goes into the Liberty file, we determine the delays using SPICE. So every standard cell is simulated. There's a circuit simulator that simulates it for different conditions and determines the delays. And then these are put into the Liberty file, and there are actually tools that will do this and generate the Liberty file for a standard cell. And as I showed you last time, in the Liberty file, there are there is a following structure. At the top of the file will be the library information, okay, the name of the library and various other attributes for the library. What are the units of all the different measures that you will see in the library? For example, what are the units of power or delay and so on, capacitance. So there is a library section in a .lib. Okay, then there is a cell section which gives specific information about each standard cell. So for example, it tells us what the function of the cell is and what is the area of the cell. And then for each pin of the cell, there is information in the .lib. And what are pin specific information? Well, timing is pin specific, right? So timing, the delay from an input pin of let's say a 2-input AND gate is dependent on which input pin we are talking about. So in a 2-input AND gate with pins, 2 input pins A and B and output Y, the delay from A to Y will be different from the delay from B to Y. And so these different, so the information for each pin and each delay arc is separately is in the pin section for each cell. So that's the sort of hierarchy of information in the Liberty file. Okay, and the timing models that are the common timing models that were used in Liberty files were lookup tables. So essentially, we each standard cell would be characterized or simulated for different conditions of input transition time and output load capacitance, and the delays determined through simulation. And then all these delays as functions of input transition and output load cap would be put into the .lib as a lookup table. And then if the actual transition time and the actual load capacitance was not exactly what was used for the simulation, then the timing analysis tools would interpolate the delay. Okay, so there would be interpolation done. And so that these kind of lookup tables are called nonlinear delay models. And they're just basically large tables of delayed numbers as functions of input transition and output load cap. Today, there are more sophisticated models which actually have equations that will be in the .lib, where pin capacitances and drive currents and so on are more accurately modeled than what you would get from lookup tables. And we use those more advanced models usually for the very advanced nodes like 7 and 5 nanometer. But for the purposes of this class, in order to facilitate thinking of delays, it's better to think in terms of non-linear delay models, and to think in terms of lookup tables, because the dependency at the end of the day is really on the input transition time and the output load cap. The other, in addition to information on standard cells, Liberty files will often contain what are known as wire load models. And these are models that are used to estimate the load capacitance of a driver. Okay, so when nets have not been physically implemented, we cannot know the resistance and capacitance of the net. But during the early phases of design, for example, during synthesis, there is a need to at least have an estimate of the capacitance that every driver drives. And since the nets have not been physically implemented during synthesis, the question is, how does a synthesis tool estimate the capacitance at the output of a driver? And there are two components to that capacitance. One component is the input pin cap of the receiving cells. So that would be known. So as the synthesis tool is creating the netlist, it knows which cells are being driven by any given cell. And so it knows the input capacitances of the cells being driven. What it does not know is the capacitance of the net itself, or the wire. And to make an estimate of that capacitance, wire load models are used. So these are also in the Liberty file, in the Liberty model. And so the wire load models are not cell specific, they're general to the library. And what they do is they make estimates of wire capacitance or net capacitance as a function of what is called as fan out. And fan out simply means the number of cells being driven by a driver. So any driver driving many cells, the count of cells being driven is called the fan out. And the wire load model will give a capacity, will give an estimate of the capacitance of the wire as a function of the fan out, the number of receivers being driven by a driver. So that's pretty much what I wanted to say about the .lib format. And as you actually do designs, you will get more familiar with that format. It's a very critical format to get to understand.